In this video, we're going to introduce the idea of thin lenses. So these are basically like lenses that would be in your glasses or in a microscope or in any other kind of optical instrument. And the basic idea is that you have this kind of curved piece of glass that refracts light in a specific way. This lens here that I've drawn is called a converging lens, and we will see why that is. In the end, it turns out that it causes light to converge onto one single point. So the basic idea of a converging lens is that if we have light rays entering this lens and all of the light rays are parallel, so this is all light entering the lens. As the light passes through the converging lens, it is refracted, and we're not going to draw the details of the refraction on this picture here. We'll get into that in just a minute. What happens as the light passes through the lens is that it is bent in such a way that all of the beams of light that were initially parallel meet at a single point here, and this is called the focal point. So it's called a converging lens because all of the light that is initially parallel entering the lens converges at a single point. And then of course the light continues on its way like this, right? So all of these different light rays are going to continue on their way, but they did converge at the focal point. Now, if you have light that comes straight in through the dead center of the lens, it will be unmoved and actually pass straight through the focal point as well. So this is a converging lens, and really what happens is that the light is bent at each of the interfaces. This is using Snell's law, like we've talked about. The idea is that each time light hits one of these interfaces, it is refracted, it changes direction, and the converging lens is set up in a very specific way with this kind of rounded structure such that you get this exact convergence of all of your light beams due to this bending of the light, this refraction. Now, to see how the converging lens actually works, we are simply going to look at three different spots on the lens, and we're going to trace the path of light as it passes through these three locations. So first, we are going to look at light that passes kind of near the tip of the lens here. We're going to look at light that passes near the tip of the bottom of the lens. And we're going to look at light as it passes straight through the center of the lens. And we're going to see how light behaves differently as it passes through these three parts of the lens. Because we want the light to be bent a lot when it passes near the top of the lens, because it has to come down towards this focal point. We want light to be bent a lot when it passes near the bottom of the lens, and we want light to be completely undeflected as it passes through the center of the lens. And so we're going to just look at those three locations and make sure that they are doing, at least qualitatively, the thing that we want them to do, that is bending the light toward this focal point. So let's begin by looking at the top of our lens here. And we're going to make a simplified model of the top of the lens. So what I mean by that is that I'm simply going to draw the top of the lens as a simple triangle. So the lens really has a curvature to it, but dealing with the curvature of the lens is more complicated than what we need to do. We're simply trying to prove that basically it will bend the light here in this kind of downward direction. So what we're going to do is we're going to trace out using the ideas of Snell's law. We're not actually going to do any of the math of it at this point. What light would look like as it enters this kind of a triangle, where inside here, again, this region is all filled with glass, and then outside of it is air. We remember that the index of refraction for glass is 1.55, and that the index of refraction for air is 1. The other thing that we need to remember is that as light passes from a medium in which it moves slowly to a medium in which it moves quickly, that light will bend in a specific way. So let's just quickly do a flat case just to remind ourselves of how this works. So let's say that we have a boundary. I'll make the boundary vertical here. So I have a vertical boundary, and I have light entering at some angle. I'm not going to worry about the reflected light. I'm only going to worry about the refracted light. I'll say that this is air and this is glass. And I will draw my normal because I always measure angles relative to the normal. All right, so what's going to happen is as my light leaves the air and enters the glass, it is going to bend toward the normal. That is, the light is going to leave at some angle theta 2, which is less than theta 1. That is as light moves from air to glass. And we remember we can think about this as kind of like a scooter, like a Segway scooter. If we have our two wheels that hit the slow medium, the wheel that hits the slow medium first slows down. The other wheel continues to go faster, and so we actually end up turning toward the normal as we hit this medium. Go back and watch the original Snell's Law video if this doesn't sound familiar to you. Now let's use this information to analyze what happens as the light passes through the top of our lens. So we are interested in light beams that are coming in horizontal. So we will have our incident light. And if we want to analyze what happens to the light as it hits this boundary, we need our normal. Our normal always passes through the point of incidence, the place where the light hits the boundary, and is always perpendicular, makes a 90-degree angle with the boundary. Okay, so we said here that when the light hits the boundary, if it is starting in air, which it is, and moving into glass, so it's moving from a medium where it moves fast to a medium where it moves slow, it's going to bend toward the normal, which means that we should have the light leave. Try to make this reasonably accurate here. At some angle that is shallower with respect to the normal, right? So it bent toward the normal as it hit this boundary. Okay. So now what's going to happen is that the light is going to continue on its path here. It's going to go through the glass, and then it's going to hit this boundary. So light comes straight in, bends toward the normal as it moves from a slow to a fast, and now it's going to move from the slow glass into the fast air, and we need to find out what happens at this boundary. All right. Well, again, we need the normal, but we need to have the normal to this boundary here. So I'm going to draw a different normal line here, which passes through our new point of incidence and is perpendicular to our new boundary. Now, just like as light moves from air into glass, it bends toward the normal. As light moves from glass into air, so we could simply reverse this picture and see, oh, if the light starts in glass and moves towards air, it tends to bend away from the normal. The exiting angle is steeper than the incident angle. So we can we have this, I'll draw it in green here just so we can see. So if the light continued on its straight line path, so this is not actually where it goes, that's just a continuation of its straight line path for reference. So we know that the light bends more away from the normal than that, which means that it is going to exit at some other angle here, which will be larger than its incidence angle. And what we have to compare, not this angle here. I'll actually erase this. When we are dealing with this boundary here, we are comparing, I'll call this theta 3 and this theta 4, right? So when we say that the light is bending away from the normal here, we are comparing the incident light at this boundary, the angle that that has relative to our normal at that boundary, with the angle of refraction, the angle relative to the new normal of the exiting light. So in this problem, we really have two sets of angles that we are comparing. So I'll call this, say, theta 1, and then this angle here, the angle between this normal, I'll call that theta 2, which is just this little blue line there. So as I hit this boundary, I have a theta 2 that's smaller than theta 1 because I'm bending toward the normal. And as I hit this boundary, I have a theta 4 that's bigger than theta 3 because I'm bending away from the normal. Now, the important thing to note here is, remember, we want our lens to cause light at the top to bend down toward the focal point. And that's exactly what happens. Light that enters the lens here, moving horizontally, leaves the lens at a downward tilt. Now let's do the same idea with the bottom of the lens. So here I've just drawn our lens and we're just taking the very bottom of the lens and kind of blowing it up. Again, we're not going to deal with the curvature of the lens. We're simply going to assume that the sides of the lens are completely straight, just for the simplicity of our model. Okay, so again, we're going to be interested in light that is coming horizontally into the lens. And we want to see that the light is bent upwards because we expect the focus to be somewhere up in this region, right? So we want the light to bend toward the center of the lens. Again, we're going to be interested in our incident light. So this is our light that is coming horizontally into our lens. We have air on the outside, glass on the inside. We are also going to need our normal to the surface we are interested in. So I will draw a normal here, which is perpendicular to our boundary. And the light is, again, as it moves from air into glass, is going to bend toward the normal. So it's going to come in at some angle and then leave at a more shallow angle. It's going to come in and bend toward the normal. And we can do the same thing on the next boundary, where we draw a new normal vector. And the light bends now away from the normal because I'm moving from glass into air, and the light bends away from the normal. So this one I have a little harder time with, so I'm going to again draw my straight line continuation. That's where the light would keep going. And the light needs to leave further from the normal than that. Again, I have skipped all of the calculations to know exactly what these angles are. If I gave you some geometry of this slice, say the angles at these two boundaries, you could actually calculate where the light goes as it leaves. But again, what we're interested in here is that the light comes in horizontally and is directed upwards toward where our focal point should be. Okay, as a final note, what we are going to do is we are going to look at the exact center of the lens, which is actually going to be by far the easiest thing we've looked at. All right, so I will redraw the lens here. So this is our converging lens, And we are going to just look at the dead center of the lens here. So the way I would draw that is simply two straight lines, where inside is glass and outside is air. Now, as light comes in, well, it doesn't get bent at all as long as it comes in perpendicular to the boundary. We can see this very simply using Snell's law. If I do n1 sine theta 1 equals n2 sine theta 2, well, in this case, our theta is the angle between our incident light here and the normal, which I will draw kind of right on top of it here. So I have two lines that point in exactly the same direction, which means that theta 1, our incident angle, is 0. And if we remember our trig, the sine of 0 is 0. So the left-hand side is 0. The only way to make the right-hand side 0 for some arbitrary n2, or n2 is 1.55, for example, for glass, is to make the sine of theta 2 0. What has a sine of 0? Hey, it's 0 degrees that has a sine of 0. So the light is going to go straight through this boundary. Again, it's going to hit this boundary at a 90-degree angle, be unrefracted there as well, or undeflected, no change in its direction, and it's going to move straight through. So what we have seen is that light at the bottom of the lens gets directed upwards, light in the middle of the lens gets directed or doesn't get redirected, and light at the top of the lens gets directed downward. And so we can just redraw our original picture of the thin lens, which I will do briefly here. So we have our lens, and as light passes through, and I'm again not going to draw the details of it in terms of where it actually bounces, we get that all of the light rays converge here. And the curvature of the lens is actually to make sure that not just near the tips or not just at the center, but anywhere the light comes through, it is going to be redirected in just the right way such that it passes through the focal point there. And we can actually change this distance to the focal point, which normally is denoted as f, the focal, it's called the focal length. We can change this focal length of the lens by either making the lens thinner, right, with less curvature, or wider with more curvature. Again, we call this a converging lens because it causes all light that passes kind of horizontally through it to converge to one location. We also will think about what's called diverging lenses. Diverging lenses kind of look like an hourglass or a capital I or something like that. And they are set up, we'll call them a diverging lens. They are set up such that all light that comes horizontally through spreads out. So if I have a light beam here, it will move away. If I have a light beam through the center, and if I have a light beam here. And these lenses are set up such that actually if you trace backwards these beams as they spread out, they actually all converge at a focal point here, so we can have some focal distance as well, even for a diverging lens. Though the light never actually passes through the focal point, it is a kind of tracing backwards of the light's path. So the light is really following these blue lines, but we can get a focal point for the diverging lens by tracing back the light's path. So I'll draw in 2 more light beams here just to show kind of how this works. That shouldn't quite be parallel here, so it should be somewhat like this, and there should be another one here that leaves somewhat like this. And if we trace back these light rays as well, they will meet at the focal point here. So we have 2 different types of lenses that we are going to deal with in this class. Converging lenses where light actually converges to a single point, and diverging lenses where light is spread out, but we can still define a focal length by tracing the path of the light backwards to this focal point for the diverging lens. In the next video, what we're going to do is we are actually going to come up with the mathematics for finding out how the light converges and actually forming images using this light.